You ever hit the undo button and just wonder? How does your computer perfectly remember every single step you just took? Well, the secret is one of the most fundamental ideas in computer science, the stack. It's a really simple concept with enormous power, and it's working behind the scenes in pretty much everything you do. Seriously, think about it for a second. Whether you're undoing a typo in an email or hitting the back button in your browser, your computer just flawlessly retraces your steps. How does it keep that history in perfect chronological order? Well, the answer lies in a data structure you use every single day, probably without even realizing it. So the whole concept boils down to one simple rule: LIFO. That stands for last in, first out. And the easiest way to picture this is with a stack of plates, right? When you're putting clean plates away, you place the newest one right on top. And when you need a plate, which one do you grab? The top one. The last plate you added is always the first one you take off. Simple as that. And this LIFO idea is absolutely everywhere. We just talked about the undo history in your document or your browser's back button. See, each new web page you visit gets placed on top of the stack. When you hit back, you're just popping that top one off to reveal the page you were on before. It's an incredibly intuitive system once you see it. Okay, so what makes a stack so darn effective? It really all comes down to its very strict set of rules. You can't just reach in and grab whatever you want. It has a very specific and very limited set of operations. And that's what makes it so incredibly efficient. There are really only 4 main things you can do with a stack. You can push a new item onto the top. You can pop the top item off. You can peek at the top item, just to see what's there without removing it. And you can check if the stack is empty. That's it. This simplicity is its secret weapon. And this right here, this highlights the stack's biggest limitation, which is, funnily enough, also its greatest strength. You are forbidden from reaching into the middle of the stack. You can't see, you can't touch any element except for the one at the very top. That strict restriction is exactly what makes it so predictable and so fast. And that restriction leads to this incredible benefit: speed. I mean, think about it. To add or remove a plate, you only ever touch the top. You never have to shift the whole pile around. In programming terms, this means that push, pop, and top are blazingly fast. It doesn't matter if your stack has 10 items or 10 million. The operation takes the exact same tiny amount of time. We call this constant time, or O1. So how do we actually build one of these things in our code? Well, programmers generally rely on 2 common blueprints to construct a stack. Let's peek under the hood and check them both out. On one hand, you can use a simple array. It's really straightforward, super fast, but you have to decide on its size ahead of time. And if you fill it up, well, you're stuck. On the other hand, you could use something called a linked list. This is way more flexible. It can grow and shrink as much as you need, but it's a bit more complex to set up. It's that classic trade-off between simplicity and dynamic power. Now, no matter how you decide to build it, you have to watch out for 2 critical errors. Overflow, that's what happens when you try to push an item onto a stack that's already full, like that fixed size array we mentioned. And underflow is when you try to pop an item from a stack that's completely empty. Good programming means you always check for these cases. Okay, so we've talked about plates and undo buttons, but now we get to the most important job a stack has. It's happening deep inside your computer right now. This simple data structure is the absolute backbone of how your programs actually run. This is something called the call stack. Every single time your code calls a function, the computer pushes a little packet of information about that function onto this internal stack. You can think of it like the computer is leaving a trail of breadcrumbs so it always knows how to get back to where it was. Each of these breadcrumbs is called a stack frame, and it contains everything that function needs to do its job, all its local variables, any parameters it was given, and most importantly, the return address, the exact spot in the code it needs to jump back to when it's finished. Once the function is done, its entire frame gets popped off the stack, and the program continues right where it left off. Pretty clever, right? And this is where that infamous error message comes from. If you have a function that calls itself over and over again, a process called recursion, it just keeps pushing new frames onto the call stack without ever popping any off. Eventually, you just run out of memory, the stack overflows, and your program crashes. Sound familiar? Okay, so now that you get the theory, the good news is you don't have to build all this from scratch every time you need it. Let's look at the easy, modern way to use stacks in your own C++ code.
C++ provides this fantastic tool right out of the box. It's called std stack, and it's part of the standard template library, or STL. It's a pre-built, highly optimized, and safe container that handles all the nitty-gritty details for you. This means you get all the power and speed without having to worry about the low-level stuff. Honestly, it's the professional's choice.
But to save you some future headaches, please be aware of these common pitfalls. The number one mistake by far is trying to pop or peek at an empty stack. It will crash your program, guaranteed. Also, remember what a stack is for. Don't try to use it if you need to search for an item or access things randomly. That's just not its job. So the real key is knowing when this tool is the right one for the job. Do you need to reverse a word? Perfect. Push each letter onto a stack, then pop them off. Need to implement an undo feature? Stack is your best friend. But if you need to search for a specific piece of data or access elements by their position, you're going to want to use a different data structure. All right, to wrap it all up, let's lock in these 4 crucial points. A stack is defined by its LIFO rule. Last in, first out. Its core operations are constant time, which makes it incredibly fast. Access is always restricted to the top element only. And finally, it's not just some abstract idea. It's a fundamental system that powers every single program you run, all thanks to the call stack. So, from the undo button to the very core of how your code actually executes, the stack is a simple, elegant, and really powerful concept. Now that you understand how it works, you'll probably start seeing it everywhere. So think about it. What else in your digital life might be secretly powered by this simple, last in, first out idea?